Hello, in this video I will discuss the type of isomers called diastereomers. It turns out that diastereomers are simply stereoisomers that aren't mirror images. That's as opposed to enantiomers that we saw in the last video, which are stereoisomers that are mirror images. So it's easy to distinguish between them. Diastereomers are not mirror images, enantiomers are mirror images. But we really need to decide on what do we mean by stereoisomers. But the stereoisomers are always one or the other. So what do we mean by stereoisomers? Well, just to remind you, they are isomers that differ from each other not by what atoms are connected to what atoms. Those are called constitutional isomers. But stereoisomers are ones that simply differ from each other in their arrangement in space. In some cases, some of those are rotational or what we call conformational stereoisomers. They also can have enantiomers and diastereomers, and the definition is the same. If they're mirror images, then they're enantiomers. If they're not mirror images, then they're diastereomers. But we're going to limit ourselves, at least for now, to just configurational isomers. In other words, ones that are permanent. They can't be turned into each other by rotating around single bonds. And so there are enantiomers and there are diastereomers. And we explored in the last video pretty extensively what enantiomers are. We'll refer to that again in this video as well, in contrast to what diastereomers are, which are not mirror images. Whenever we're comparing isomers, we're always comparing two molecules. But diastereomers specifically are two molecules, very often with more than one stereocenter. So imagine some molecule that has a stereocenter somewhere in it, in other words, a carbon with 4 different groups, and another stereocenter also somewhere in the molecule, also having 4 different groups attached. That would be 2 stereocenters in the same molecule. Then you have the possibility of diastereomers. Now, the reason I said often here is because it turns out there are other kinds of diastereomers that don't have any chiral carbons, or that may only have 1 chiral carbon. But the kind we're going to deal with for the moment are those that have more than 1 stereocenter. Now, the 2 molecules that we're comparing each one may have an enantiomer. So this molecule may have an enantiomer, and this molecule may also have an enantiomer. But remember, these are not mirror images of each other, so each one may have its own mirror image. If that's true, then all the chiral carbons in one enantiomer will be the opposite of the chiral carbons in the other enantiomer. So if you have all R's in one enantiomer, you'd have all S's in the other enantiomer. If you had an R and an S in one enantiomer, then you have an S and an R in the other enantiomer. But what we're talking about is diastereomers. Each molecule may have then a diastereomer. One or more chiral carbons in this diastereomer is the same as one or more chiral carbons in this diastereomer, and one or more chiral carbons in this molecule is different from one or more of the chiral carbons in this molecule. So some are the same and some are different. That's the key. And because some are the same and some are different, they can't be mirror images of each other. If they're going to be mirror images, they all have to be opposite. So here's a molecule. It's called 3-bromo-2-butanol. You don't really have to worry too much about the naming system at this point. We'll learn naming system for alkyl halides and naming system for alcohols later on, but I don't think you have too much trouble figuring out that particular name. Anyway, notice that this particular molecule has 2 chiral carbons. So this molecule, which I've called carbon number 2, has a hydrogen, an OH group, a methyl group, and then this CHBr-CH3 group. So a hydrogen and an OH, a CH3, and a CHBr-CH3 group. So this carbon has 4 different groups, so it's a chiral center. This carbon also has 4 different groups. What are they? A hydrogen, a bromine, a methyl group, and then this whole big group over here. So 4 different groups on that carbon as well. So this is an example where we may have diastereomers. If you have 2 or more chiral carbons in the same molecule, then you can get diastereomers. Now, let's draw the stereoisomers of 3-bromo-2-butanol. All you really need to do is have a skeleton of this type with 2 different tetrahedral carbons in the same molecule. And by the way, in this particular case, let me back up. In this particular case, the 2 chiral carbons are next to each other. So this is a chiral carbon and this is a chiral carbon. That's not necessary for this discussion to work. As long as you have 2 chiral carbons somewhere in the same molecule, then one of them could be R or S and the other one could be R or S, and then you have the possibility of diastereomers. But in this case, they happen to be right next to each other, so the skeleton will work in which that carbon is a chiral carbon and that carbon is a chiral carbon. And notice that on one of them, let's say this carbon right here, we're going to have a hydrogen, a bromine, a methyl group. And on this carbon next door to it, we're going to have a hydrogen, a CH3, and an OH. So what I want you to do is on this carbon, put a hydrogen, a methyl, and a bromine. And on this carbon, put a hydrogen, a methyl, and an OH. And that will then be one of the possible stereoisomers of 3-bromo-2-butanol. But to be consistent, so that everybody's going to get the same answers, or that everybody's will look the same at least, what we want to do is make sure that everybody is going to put on this carbon hydrogen, bromine, and methyl somewhere, and on this carbon hydrogen, OH, and methyl somewhere, and then do it again on this one, hydrogen, bromine, and methyl, and on this one, hydrogen, OH, and methyl, and then on this one, same thing. So put the bromine on this carbon, OH on this carbon, bromine on this carbon, OH on this carbon, and so on, just to be consistent. And then also to be consistent, and to make it easier for us to determine R's and S's, let's go ahead and make that group on the dotted line a hydrogen, and same thing here, make that one a hydrogen. That way we'll know that the hydrogen is pointing away from us, and we can then do the R's and S's easily. So take a minute, stop the video, and just put a hydrogen there, and then a bromine or a methyl on those two. Hydrogen there, and then an OH and a methyl on those two. And you'll find, if you look carefully, that there'll actually be 4 different ways that you can do that. So go ahead and do that, and then we'll see if your answers are the same as my answers. So what I've done here is I've put a hydrogen on the dotted line, a bromine and a methyl there and there on this structure. Here, I put the hydrogen on the dotted line and a bromine and a methyl, but I switched the bromine and the methyl. Here, I put the hydrogen on the dotted line, and the bromine and the methyl are the same as they are here, but the OH and the methyl that I put on this carbon are not the same. So this carbon is the same as this carbon, but this carbon is different from this carbon. This carbon is different from this carbon, but this carbon is the same as this one. This one is the same as this one, but they're different from these two. So now your answers, the 4 structures that you have in front of you on your paper, hopefully should be the same as these 4 that I have right here. Now they may not be in the same order. In other words, the one that I have in the upper left corner, you may have somewhere else among these 4 structures. And this one that I have in the upper right corner, you may have somewhere else among these structures. But among your 4, you should have these 4 structures. Why should we all have the same 4 structures? Well, it turns out that if there are 2 chiral carbons, then there are 4 possible stereoisomers that you can draw. And so there's a rule of thumb that tells you how many possible stereoisomers there are based on how many chiral carbons there are. That will usually give you the right answer. It turns out in some cases it won't, and we'll talk about why in the next video. Pretty much, if there are 2 chiral carbons, you should get 4 stereoisomers, and that's what we have here. So check your answers and make sure you have these same 4 structures somewhere among the 4 that you drew. Now, let's go ahead and assign R's and S's to each chiral carbon. So right here on this structure, assign that carbon an R or S, assign that one an R or S, assign that one an R or S, assign that one an R or S, and so on. And what you'll find is it's relatively easy because the hydrogen is already pointing back in each case. So you just have to go 1 to 2 to 3 and see whether it's clockwise or counterclockwise. Okay, so take a minute and do that. Okay, let's move on. Here are the answers. So notice that this carbon is hydrogen's already pointing back. That's the highest priority, that's the second highest priority, that's the third highest priority, so it goes 1 to 2 to 3 in a counterclockwise way, so therefore that is an S configuration on that particular carbon. Similarly, this one is an R. So somewhere among your 4 structures you should have the carbon with the bromine being S and the carbon with the OH being R. Notice that this one, since that carbon is the same as that carbon, should still come out to be S, which it does. 1 to 2 to 3, still S. But because this carbon, the OH and the methyl group are switched, it went from being R to being S. So this is what's called an SR isomer. This is what's called an SS isomer. Actually, technically this should be called an RS isomer because the OH is on carbon number 2 and the bromine's on carbon number 3. So the one with the lower number among the carbons in the chain should be listed first. So this is an RS isomer. This is an SS isomer. This is an RR isomer, and this is an SR isomer. So among your 4, you should have those 4 sets of R's and S's. Okay, now what I'm going to do is redraw them again in such a way that they actually look like mirror images. So what I'm going to do is take this structure and I'm just going to turn it in space in such a way that it's going to look like a mirror image of this. Or excuse me, actually take this one and turn it in space so it's going to look like a mirror image of this. And this one, turn it in space so it's going to look like a mirror image of that. And by the way, I know this is the mirror image of this because this is RR and this is SS, and RR has to be a mirror image of SS. Here we go. Here they are drawn again in a slightly different way. I've turned some of them around. Notice that this is now drawn in such a way it looks like a mirror image of this and vice versa. If there's a mirror plane in here, then this OH looks in the mirror and it sees an OH right there. Methyl group looks in the mirror and it sees a methyl group right there. Hydrogen looks in the mirror and it sees a hydrogen right there. This methyl group, which is back away from the mirror, looks in the mirror and sees way back inside the mirror on the other side a methyl group back there. This bromine looks and sees a bromine there. This hydrogen looks and sees a hydrogen there. So hopefully you can all see that these are in fact mirror images of each other. And likewise, these are mirror images of each other. So that methyl sees that methyl across the mirror, this OH sees this OH across the mirror, this hydrogen sees that hydrogen across the mirror, and so on. Notice this methyl group sees that methyl group, and so on. And of course, it should be that RR is the mirror image of SS, which it is, and RS should be the mirror image of SR, which it is. Okay, and if you haven't quite figured out why those are mirror images, and you haven't quite figured out how the letters correspond to the mirror images, study those four molecules for a minute until you see the relationship between them. Let's go back and name these. Since this is carbon number 2 and this is carbon number 3, we're going to call this one 2R, 3S, because carbon number 2 is R and carbon number 3 is S. So 2R, 3S, 3-bromo-2-butanol. This is going to be 2S, 3R. Then this is just RR, and we don't need to say which one's 2 and which one's 3 because they're both R, and this is then SS. Okay. But in all four cases, it's 3-bromo-2-butanol because that's the main IUPAC name. These things in front with the R's and the S's are what are called stereochemical designators, much like cis and trans are stereochemical designators. They just specify which stereoisomer are you talking about. Okay, now what I want you to do is study these two molecules and see if they are enantiomers or diastereomers. It has to be one or the other. If they're not the same as each other, which they're not, obviously the names are different, if they're not the same as each other, but they are stereoisomers, which they are, then they have to be either enantiomers or diastereomers. So study it and see if these two are enantiomers or diastereomers. Basically, the question is, are they mirror images or not? Okay. Then study these two and see if they are enantiomers or diastereomers. Then study these two and see if they are enantiomers or diastereomers. And study these two and study these two and study these two. So there's all the different possible combinations, because you're always comparing pairs of molecules when you're looking for isomers. Okay? So go ahead and label all those, and then we'll switch to the next slide and see what I got for my answer. Okay, so the first two are enantiomers. SR is an enantiomer of RS because they're mirror images, and that's the definition of enantiomers, is mirror images. Same thing here. These are also enantiomers because they are mirror images. These two, on the other hand, one from this set and one from this set, are diastereomers because these are clearly not mirror images. SR can't be the mirror image of RR, and similarly, these two are not mirror images, so they are diastereomers. RS is a diastereomer of SS, and similarly, these two are. SR is a diastereomer of RR, and these two are diastereomers, so on. Now, what about physical properties? We know that enantiomers, if you have two enantiomers in two different bottles and you measure their physical properties, melting point, boiling point, density, blah, 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 that they're the same. In other words, one enantiomer has exactly the same properties as the other enantiomer, except for optical rotation. Remember, with optical rotation, they rotate plane polarized light by the same amount, but opposite ways. So one might be negative 32 degrees, the other one would be positive 32 degrees, and so on. But that's the only way they differ from each other in terms of physical properties. What is true about diastereomers? Well, as it says here, diastereomers are different in every way in terms of their physical properties. No relationship between their boiling points, no relationship between their melting points. They have different diffractive indexes, they have different densities, and so on. And they have completely different optical rotation. So if one of them happens to be, let's say, plus 14 degrees, the other one could be minus 32 degrees, or plus 5 degrees, or some other number, and there's no way of predicting which one will be positive and which one will be negative among two diastereomers. They might both be positive, both be negative, one positive and one negative. There's no relationship between them. So basically what I'm saying is that diastereomers are different compounds in every way. They're easily separated from each other, and they have different properties. So for example, I've drawn three molecules here. Notice that this is a chiral carbon, it has an S configuration. This is a chiral carbon that also has the S configuration. Its melting point is 171. This is the same molecule, but it's the RR. So what's the relationship between these two? SS and RR. Those are enantiomers, so they turn out to have the same melting point, which is exactly what we would expect. This molecule is an RS molecule, and therefore it's a diastereomer of this one, and it does not have the same melting point. This one happens to be 145, and by the way, I looked these up, and these are correct. Those are both 171, and that's 145. So like we would predict, because they're diastereomers, they have different physical properties. Now, you can also look at enantiomers and diastereomers on Fisher projections, and this is one of the ways in which Fisher projections are particularly useful. Remember what a Fisher projection does. It assumes that you know that anything that's on the crossbar is coming out towards you, in other words, on wedges. and whatever's on the vertical bar is going away from you, so a dotted line. So that's going away from you, as is that methyl group going away from you. And these two groups, the hydrogen and the OH, are coming towards you. These two groups, the hydrogen and the bromine, are coming towards you. Now you can go ahead, I haven't done it, but you can go ahead and assign R's and S's to each of the carbons in this set of 4 molecules, and same thing here. And of course these are the same as these, so whatever you get for this, you should also get for that. You might want to go back and review how do you do R's and S's on Fisher projections. But notice that these two, it's very easy to tell the way they're drawn that these are mirror images of each other, and therefore these are enantiomers. Same thing here, these are clearly mirror images of each other, so these are enantiomers. So any of these two is a diastereomer of any of those two. Now, what about cis-trans isomers? We talked about them in an earlier chapter. If you have two groups on a ring, but not on the same carbon, then they both may be up, they both may be down, or one may be up and one may be down. If they're both on the same side, we call them cis. So these two molecules are both called cis. But the question is, are these the same as each other or not? And the answer is no, they're not. No matter how you turn them, rotate them, flip them upside down like a pancake or whatever, you will never make these look the same as each other. But they are in fact mirror images of each other. So these are really enantiomers. And you can do R's and S's on these carbons, and you can find out that whatever these two are, these are exactly the opposite. These two, though, are trans, so these two both have the same groups on the same side. This one both down, this one both up. But this one has one up and one down, so it's the trans isomer. This is also a trans isomer. So these are, in fact, also enantiomers of each other. This one may be a little bit trickier for you to see, but the fact is these two are not the same as each other and can never be made to look the same as each other. You might say, well, what if we just take this one and flip it like a pancake? Then it will have the methyl group up here and the ethyl group down here, but the methyl group will be up and the ethyl group will be down, and it will still not look the same as this. Or if you turn it this way, like a pancake, this methyl group will be down and this methyl group will be up, just like they are here, but they'll be on carbons over here instead of over here. So the fact is, if you have two groups on a ring, you can have cis and trans, and the cis ones are always diastereomers of the trans ones, and so on. So cis is always a diastereomer of trans. That's a hard and fast rule. You can remember that. Okay, so let's review the types of isomers that are possible. First of all, you have isomers in general. And again, remember, we're comparing two molecules. So these are two molecules that are somehow different from each other but have the same formula. Of that, there are two possible types. There's the constitutional, in which the order of connections is different, like, for example, N-butane and isobutane. On the other hand, you can have stereoisomers, in which the order of connections, what atoms are connected to what atoms, is the same, but somehow the shape in space is different. Now, how can the shape in space be different? Well, either because you have rotation around single bonds, in which case we call it conformational, and they can then be turned into each other, or not. And if you can't turn one into the other by rotating around single bonds, then they're more permanent isomers that can't be turned into each other, and that's what we call configurational isomers. Now what we've learned is that under configurational isomers there are two types. There are enantiomers, which are mirror images, and there are diastereomers, which are not mirror images. It's very simple. If you have two stereoisomers that are mirror images, then they're enantiomers. If they're not mirror images, then they're diastereomers. And by the way, you need to look carefully at these, because it's possible that the way they're drawn, they don't look like mirror images, but if you do some rotating and some turning in space, then you can make them look like mirror images. And if at any time you can make them look like mirror images, then they are enantiomers, even if they may not look like mirror images at first. Okay? If you can never make them look like mirror images by just rotating around single bonds and turning them in space and so on, they never will look like mirror images, then they are diastereomers. Now you need to be careful in all of these things, because sometimes molecules are actually identical to each other, so in which case they're not isomers at all, they're just two different ways of drawing the same molecule. So really there's three possibilities: isomers of each other, completely different molecules, not even isomers, or identical. In some cases you'll be given two molecules that don't look the same as each other but actually are, in which case then they're not isomers at all. So the same thing, just drawn in different ways. So I talked earlier about a rule that will tell you how many possible stereoisomers there are for a given structure, and here's the rule of thumb. If you have n chiral carbons in your molecule, then you'll have 2 to the n stereoisomers. Now that's just a rule of thumb. Turns out that in some cases there's actually fewer than that, and in some cases there are actually more than that. But as a rule of thumb, in typical molecules, if there are n chiral carbons, there will be 2 to the n possible stereoisomers. So for example, if you just have one chiral carbon, like this is a molecule with one chiral carbon, 2 to the first power is just 2, so there should be 2 stereoisomers. And that makes sense, because if there's only one chiral carbon, it can only be R or S, so you can only have an R isomer or an S isomer, and that's 2 possibilities. But if you have two chiral carbons, that's in the molecule we saw before, then there are four isomers, and that makes sense because they could both be R, they could both be S, one could be R and the other one S, or the first one could be S and the other one be R. So there's four possible combinations, so four isomers. What if there are three chiral carbons? Well, 2 to the third power is 8. Then there are 8 possible stereoisomers. There's the RRR in its mirror image SSS, and I haven't drawn any examples of that, but you could draw some if you wanted to. Then there's the RRS in its mirror image SSR. Then there's RSR in its mirror image SRS, and the RSS in its mirror image SRR. Now you might say, but isn't RRS the same thing as SRR? And the answer is, in some cases, yes. And that's why in a few cases it actually can be less than the amount protected by this rule. But if the 3 carbons are different from each other, then RRS is not the same as SRR. So there's a maximum of 8 isomers. There might actually be fewer than that. Actually, in a few cases, there might be more than that, as I suggested. But the rule of thumb says that at least on a basic level, there should be 8 isomers for 3 chiral carbons. And similarly, if there's 4 chiral carbons, there should be 16 isomers. Many simple sugars have 4 chiral carbons and therefore 16 isomers. And if there's 5 chiral carbons, there's 32 possible isomers. There are other sugars that have 5 chiral carbons, and so there's actually, in some cases, 32 isomers of a particular sugar. And we're talking stereoisomers here. And as a general rule, if there's n chiral carbons, then there's 2 to the n isomers. Now, let's talk about chirality, because we haven't really mentioned that. But it's always hanging around in the background when you're talking about stereoisomers. So how does the existence of enantiomers and diastereomers relate to the idea of chirality? There's 2 sort of rules or generalizations that you can make. First of all, if a molecule is an enantiomer of another molecule, so in other words, you have 2 different molecules that are mirror images, remember enantiomers means mirror images, 2 different molecules that are mirror images, but are not the same as each other, because if they're the same as each other, then they're not isomers at all. But if they're mirror images that are not the same as each other, then they're called enantiomers, and by definition, they will always be chiral. Why is that? Well, because what's the definition of chirality? Not the same as its mirror image. So if you have 2 things that are mirror images but aren't the same as each other, then by definition they have to be chiral. So if it's an enantiomer of another molecule, then it has to be chiral. And vice versa is also true. If a molecule is chiral, then it has to have an enantiomer, because what's the definition of chirality? Not the same as its mirror image. So if it's chiral, it can't be the same as its mirror image, which means there are 2 different mirror images, which means there are enantiomers. So chirality and enantiomers always goes together. But here's where it gets really interesting. If a molecule is a diastereomer of another molecule, then they both may be chiral. One may be chiral and one not chiral, or in some cases neither one of them is chiral, and that seems impossible. How can you have 2 molecules that are diastereomers of each other but aren't chiral? So it just seems impossible. Well, it's not impossible. It's a very interesting phenomenon, and we'll talk about that in the next video. Thank you for your attention.